Hi, this is Vaishak, and welcome to the first episode of Nodes. Today, we are going to learn about autoencoders. Now, what are autoencoders? Before getting into the technical details, I thought I'd give you an intuition. This is what I found on the internet. It's a very simple explanation. Uh, the analogy is, let's say if you wanted to capture a Pokemon, a Snorlax, which is snoring off comfortably in the wild, and you decided to capture it. So you throw a Pokeball at it, and hopefully it's captured. And then later, when you want to use it for battle, you wanted to release it, you just throw the Pokeball out, and out comes the Pokemon in its full glory. This is essentially sort of the idea behind autoencoders. But the thing to notice, as far as autoencoders are concerned, is this is not quite how it works. This is not what they achieve, but this is the aim. That is to reconstruct the input. In other words, whatever you send the autoencoder, it must give you back, or at least try to. So, in the case of the Pokemon, you don't capture the entire Pokemon, you squeeze it into a small Pokeball, you compress it, and then later release it into its full, expanded, inflated form. So, this is what an autoencoder tries to do. It tries to compress the input into a convenient, tiny little representation, kind of like our file compressors do. But this is more machine learning. So, let's do it. This is how it looks like. On the top row, you see the MNIST digits, which are a collection of handwritten digits from 0 to 9. And on the bottom, you see the reconstructed MNIST digits from the top, the corresponding digits. And in the middle, you see the latent or hidden representations, also called the latent code. This is what the autoencoder does. It encodes the inputs in the top row into a tiny latent representation. So in this case, the input has 784 features. It's a 28 by 28 grayscale image. So there are 784 pixels, but in the middle, in the compressed representation or the latent code, you have 32 bits or 32 features as they are called. And then, of course, it tries to sort of get back the inputs from these 32 bits of information. So this is what an autoencoder does, and this is what it looks like. So essentially, what we try to do is in an autoencoder, so on the left, you send an input, whatever input that may be. In the middle, you have the compressed latent representation, and on the right, it's again inflated back into hopefully something similar to the input. So, what happens in an autoencoder essentially is through a process of transformations, you sort of squeeze successively the input into smaller and smaller representations until finally you get a latent representation of the desired size. And on the decoder, you do the inverse. That is, you take the latent compressed representation and through a successive series of transformations, continuously increase its features, its information, and then arrive at the full output. So this is the autoencoder, and as you can guess, the name is because it's an encoder and a decoder kissing. So let's make an autoencoder. So what I've done is I've written an autoencoder class which sort of encapsulates this behavior of an autoencoder. That is, it takes in an encoder module and a decoder module, and what it does is, you see in the forward function, it gives you the latent representation, or rather, it gets the latent representation Z from the encoder while passing in the input X. And then, of course, it sends this latent representation onto the decoder, and you get back the reconstructed output. x re. What you'll notice here is something very curious. That is to say, in after the final layer of the decoder, after the decoder gets the output, what you do is you send it through a tannage activation, and what that essentially does is it squeezes the outputs in between -1 and 1, which is exactly what we want, because the data that we loaded, the MNIST digits that we loaded, were normalized between 0 and 1. So, in some way, we are making it easier for the network to learn this representation or this function, this identity function. And then what we do is, additionally, because it's an image, it's a four-dimensional tensor, what we do is, finally, we bring it back to its input shape, just in case it's flattened, just in case we have linear or feed forward layers, in which case it's flattened before sending it through the layers. So this is just an extra step. What I've found is, if you if you have a tannage activation right at the end, so that you make it easier for the network to learn this representation, and on the encoder side, if you don't have any activations on the final layer, that is, if you make the final layer just a linear projection, then it helps the autoencoder learn. So this is just a small observation to make it learn easier. But of course, there is a caveat, and the caveat is, if you use a tanh function, beware that tanh and sigmoids are not in fashion anymore. It's all about ReLUs and all those exotic new functions such as CellUs. I don't know how many people use them, but tanh I haven't seen those used much. And the reason is, of course, the derivatives of the tanh function, when you want to backpropagate the derivatives, which you need to do if you want to train the network through stochastic gradient descent, is very small. The derivatives are very small near the endpoints, near the extreme regions, which are -1 and 1 in case of the tanh function. Curiously, what we have in the case of this particular data set, the MNIST data set, is the following. So let's take a look at the data set. And as you can see here, most of the pixels are black or -1, the extreme range, and most of the pixels are white in the region of interest, in the digits. So it's +1. Only the border areas are slightly gray in between -1 and +1. So what that means is, when you want the output to be between -1 and 1, or rather very near -1 and 1, the derivatives will be very, very low. So that means the network will find it a little bit hard to learn, because it has terribly small derivatives which are backpropagated. So that's a slight point to remember. Nonetheless, what I've found is, if you have the tanh function, the network learns faster and better. So let's do it. But before starting out, let's define a small neural network class. And what that class does is, you send in a sequence of sizes, including the initial size and the hidden sizes, and it constructs a successive feed-forward neural network, the vanilla type, with those latent size, hidden sizes. And it uses the ReLU activation functions for all layers except the final layer, because we want to control how the final layer behaves. So, for example, in the decoder side, we set the tanh activation. So let's first see what happens when we have just one hidden layer. So on the encoder, what we do is, we go from 784 features of the MNIST images, 28 by 28 by 1, to the latent size, which I've set to 32 here. And on the decoder side, of course, the mirror, which is, it goes from the latent size to 784. Let's optimize this for 2 epochs, and I've done that. The history of the training shows something a bit curious, which is that it's underfitting. The validation loss, which is in green, is lower than the training loss, slightly lower. So that's a very curious phenomenon which you don't normally see in neural networks. They tend to overfit, and underfitting means they are not in their full capacity. But what I suspect here is, although it's very curious, what I suspect is that this green validation loss will sort of saturate and the training loss will come further down and they'll meet eventually. So we have to train a bit more. But that doesn't matter. What matters is the validation loss eventually. And let's see what happens when we try to reconstruct. Let's see the full sequence with a set of validation images. And on the top, we have 5 such validation images. On the bottom, we have the reconstructions, and on the middle, we have the latent code. And I want you to focus your attention on the fourth row, the number 4. You see, the reconstruction is not faithful. It does not contain the entire details of the original image. It's very fuzzy. But this, in some sense, is what we want. Because if you see, if you pay close attention to the output, you'll see that the number 4 is, you can sort of make it out that it's 4. And you can make out which shape it's in, the size, the strokes, the thickness. Although you don't have the pixel by pixel exact details which go into the image, but you sort of have a fuzzy uh, sort of summary of what the image had. And this is what an autoencoder does. It extracts the essential features from the input, and those essential features are shown in the middle. In the middle, you have uh, 32 latent codes. The more red a pixel is, it means it's more positive, and the more blue it is, the more negative it is, and the white pixels are very near zero. So these are the compressed latent representations, and you can see how compressed it is. Let's try further with, let's increase the complexity because it was underfitting. Let's increase the complexity to 3 hidden layers and try the same thing. We do it for 2 epochs. Oh, by the way, I forgot to mention that the loss that we use is simply the mean square error because it's a continuous distribution. We don't want to mess around too much. So we just use the mean square error. Of course, you could use other types of losses. So, for example, if you are quantizing this image to 0 and 1, or between -1 and 1, whatever, 2 classes, white and black, then you could use the sort of binary cross entropy. Or if you are quantizing to multiple classes, maybe the categorical cross entropy with the softmax layer. It's your choice. But in regular literature, what I've seen is that the autoencoders almost always use the regular mean square error. Okay, so the same thing, we optimize for 2 epochs and we see that the losses are in fact a little bit higher than the previous simpler neural network. Why is that so? It's because the network is more complex. Essentially, this network, if you calculate the one with one hidden layer, it has somewhere around 50,000 parameters, I guess. And this, the 3 layer network, has almost double the number of parameters. So it takes much longer for the network to converge on a solution. So if you trained it for longer, if you trained it for say 10 epochs, both the networks, the one with one hidden layer and the one with 3 hidden layers, what you'll observe is that the one with 3 hidden layers performs better because it has more capacity to model the data. Something very curious is, if you've noticed, I've jumped straight from one hidden layer to 3 hidden layers, and that's because I like symmetry. So the encoder and the decoder are symmetric. It goes from 784 to twice the latent size, which is 64, to latent size, which is 32. And on the decoder, it does the reverse. So I didn't want any lack of symmetry, although that's an exciting direction of research, I guess. So the reconstruction, of course, it's worse than the one layer uh, neural network because the losses are higher. Nothing special. But since we're dealing with images, It'll be criminal if we don't use a convolutional neural network. So let's use a connet. And what this convolutional net does, it's very simple. On the encoder side, the convolutional net has two layers, two convolutional layers. So it goes from one channel to latent size divided by 2, which is 16 channels. And the kernel size is 3. And that's, I guess, the default kernel size in PyTorch really should, at least for the Con2D class, because it deals with images, set the kernel size to 3, the default to 3. We use stride 2 and padding 1. What that does is it reduces the image size to exactly half. And you could use max pooling. You could use stride 1 convolutions with same padding, and then you do a max pooling to reduce the image to half. And most people uh, did it at the very beginning in the era of AlexNet and BGGNet, but I don't see that used often these days, the max pooling layers. I don't know why that is the case, but it's very convenient this way. If you just want to reduce the image size, why not include it with the convolution itself? That is, use a convolution which itself reduces the image size to half, so not a separate layer. And I certainly like it. So that's the first convolution layer, and the second one does very similar. It goes from latent size by 2 to latent size, and the image size is again halved. So after the first convolution, the image size is 14 by 14, and then after the second, it's 7 by 7. So the second output, after the second convolution layer, the output is has latent size number of channels, and 7 by 7 is the image size. So we sort of flatten it to latent size by 7 by 7, and then we sort of linearly project it onto a vector of latent size 32. And that's what we do on the forward function. We go through the convolution layers with the ReLU activation, and then we finally flatten it and then pass it through the fully connected layer. On the decoder side, it's again the mirror image. So we first project through a linear layer from the latent size code to the latent size by 7 by 7. And then, of course, we inflate it and pass it through a convolutional layer, which is the same convolution. So it retains the image size. But before passing it through, we want to double the image size, which we do using a regular upsampling layer. Now, what's very interesting here is this sort of deconvolution, the opposite of convolution, increasing the resolution of the image through a convolutional layer, was done using transposed convolutions earlier. But there was a wonderful paper, I couldn't link it in this video. I'll link it in the description. The paper essentially argued that if you use transposed convolutions, you get checkerboard artifacts in the beginning of the training. And on the other hand, if you just use nearest neighbor upsampling and then pass it through a convolution and retain the image size, it's very smooth. So this is more in favor these days. So we first upsample it and then pass it through the convolution layer. So that's a convolutional autoencoder. And let's do the same thing. Let's train it for 2 epochs and see what happens. And not surprising, the losses are much lower than the fully connected feed forward neural network, because we are dealing with images, and convolution equals images, or images equals convolution, I guess. Okay, so let's see the reconstruction, and it's almost perfect reconstruction. But of course, as you can see on the fourth row, the reconstruction of the two, the loop of the two is slightly fuzzy. So the convolution does not get the details correct, the small level details correct, but it's very, very accurate. And it does, curiously, some corrections. So for example, in the second column, you see the 3 has a pixel right here. And the autoencoder does not capture this pixel because it does not think that this pixel is relevant for reconstruction. It does not think that this pixel belongs in the image. So it excludes the pixel from the reconstruction, which is very good. And already you get some ideas for extending autoencoders. So let's look at those ideas. And the ideas, broadly speaking, revolve around this idea of regularization, which we've looked at multiple times, or at least we will look at because this is the first video of the channel. Okay, so regularization means we constrain the network. We don't allow it to overfit. So there are multiple ways to regularize a neural network. Before that, let me touch on this fact, which will hopefully make this regularization part a bit clearer for you. The autoencoder squeezes the input in between, right? The input goes from the left to the right, and in between it's sandwiched, it's squeezed. There's a bottleneck, and of course, this architecture, this general idea of squeezing uh, some some vector to smaller number of dimensions is called a bottleneck or a bottleneck layer, and you see variations of it in, for example, ResNet. We look at those things very in much later videos, but for now, this architecture is called bottleneck. And what we see here is that the autoencoder is not allowed to cheat in this way. So if we, for example, have something like linear regression, which I've explored in this notebook, in this section, called naive linear regression. If you have something like linear regression where you go directly from the input to the output, what it can do is it can essentially map each pixel of the input to the corresponding pixel of the output. So it's cheating in some way. We are giving too much capacity to the neural network, so it's overfitting. It's not generalizing. So these type of squeezing bottleneck architectures of autoencoders are called undercomplete autoencoders because we are not allowing the autoencoder to complete uh, essentially or cheat. What we could also do is we could create over complete autoencoders. So we allow the network to cheat, but we restrain or we sort of impose a constraint on the network that does not allow it to cheat in some way. So the ways are the following. We could add some noise to the input. And what it does is the autoencoder learns to denoise the input. That is to say, it learns to map the noisy input where we've added artificial noise, and it maps it to the regular input. So that's how we train it. So for example, in this case, like we just saw, with the convolutional autoencoder, it understood that this pixel around the 3 here does not belong to the 3. So if this were some form of noise, pixel noise, the autoencoder would quickly learn to remove it and deal with it. So that's one way. We could also have sparse autoencoders, which is a form of regularization. Sparsity means most of the weights turn out to be 0. And we ensure it by L1 regularization, which is we constrain the absolute value of the input. So we impose a loss, which is the sum of the absolute value of the weights, not the input, the weights. So what that does is it forces the weights to go to 0. There is a competing objective, a competing loss, which drives the weights to 0. So, if the weights don't quickly adjust themselves, they'll quickly go to 0. What that means is the only weights that survive the process of training are the weights which truly matter. So that's how we could construct an autoencoder by allowing it to be over complete first, and then uh, evoking some sparsity constraint like L1. We could also have something called the contractive autoencoder, although I don't see it used much these days. What that does is it imposes a similar constraint on the gradient of the autoencoder, the gradients. So, if you train it with that additional term, which is the loss of the gradients, which is the sort of value of the gradient, something very similar to the sparsity, what happens is the autoencoder is very robust to small changes. So the gradients are very, very small, but I don't see it used these days. So that's about regularization. And since the autoencoder is primarily doing compression, it's compressing to a very small latent representation and then expanding. One could argue that the main function of autoencoders is compression to a much smaller representation. But this is exactly what PCA does. It takes a data set and it compresses the data set into some principal components. So one could argue that why have autoencoders when you already have PCA? And the reason is there's some difference between the autoencoder and the PCA. The primary difference is the autoencoder could be as non-linear, as general as you like. So the PCA is a linear mapping. The PCA learns linear manifolds onto which it can project the data in its space. The autoencoder does not have this problem. It can learn nonlinear manifolds. That's the first difference. So an autoencoder is much more powerful than the PCA in some sense. The general other difference is that the PCA is a very mathematical algorithm. There is no training process involved like uh, a neural net. There is no algorithmic training involved. There is a small mathematical function which is learned through data. So, of course, it's machine learning, it's data specific, but it's not an iterative algorithm. It's very quick. So what happens, just to give you an overview of the PCA algorithm, is that the PCA finds principal components, uh, orthogonal directions in the space of the data, along which the data has maximum variance. Why does this do it? Why does this algorithm do that? It's because when it when it projects the data onto the subspace spanned by all these principal components, what happens is along all the other directions, the variance of the data is very, very small. So the error is reduced when you project the data onto this much smaller subspace. So, in some sense, they are exactly the same. The differences in practice, what you see is if you use a linear autoencoder, which learns a linear mapping, so it's about the same as the PCA. The difference there is that the linear autoencoder does not have to learn orthogonal weights, orthogonal directions. There is no constraint. On the other hand, on the PCA, there is a mathematical constraint that it has to learn orthogonal directions. And what we observe is that along these directions specified by the weights of the autoencoder, the variances of the data are very, very similar. Okay. So that's about it with the PCA. And now let's look at some applications of the autoencoder. This is something very interesting I came across on the internet. This is by Jigar Bandaria. And what he has done is he's he's taken a different spin to the autoencoder, to the denoising autoencoder. What he does is instead of adding artificial noise to your images and then training the algorithm to remove those noises, he treats the MRI scan of the brain tissue as the noisy image. And then the algorithm is trained to separate it into these three categories. So, white matter, gray matter, and cerebrospinal fluid. These three categories. They are treated as the regular sort of versions, and the MRI scan itself is treated as the noisy version, which makes some sense. So, it's a very, very clever idea, and hopefully, it's reaped benefits. So you can see already that how a, a simple idea like the autoencoder can be used if you have a little bit of imagination in different ways, we could also use it for image search, and it's a very unique type of image search. It's called content-based image search, and you can see from from this image what it means. So suppose we have a query, not in the form of words. So for example, if I wanted to search for a burger, I instead of searching burger, I show it an image, an already existing image of a burger. And what the algorithm does is it fetches different images from its database which look very similar to this query image. And how it does this is through an autoencoder. So what happens is an autoencoder is trained in much the similar fashion that we've done, and all the images in the database of the search engine are compressed onto the encoded latent space. And then when I have a query image, the search engine fetches the image and then sends it through the encoder and finds the latent representation. And then it matches this latent representation to all the images in its database, and it ranks according to the proximity of the latent spaces. So it's a very, very clever thing. And what you observe in practice is when you do that, when the latent spaces match very closely, you see very similar images, similar uh, directions, similar shapes, similar textures. So you can see some of these images are not burgers per se, but they look kind of similar. So it's not a sophisticated version of content based image search, but it gets the job done in some ways. And there are lots of other applications of autoencoders. So let me go through a few of them verbally. Clustering, you could cluster, uh, instead of nearest neighbors or some other regular algorithm, you could use autoencoders. You could have one class classification. You could paraphrase a text. So this is really interesting. If uh, you could send a text as the input to an autoencoder, and it learns the hidden representation or a summary of the text. You could use that to summarize the text or reconstruct the text in some different way. So for example, you add a little bit of noise, and what it does, it changes the words slightly so that the meaning or the essence is retained, but the words or the way of conveying that meaning is slightly changed. So paraphrasing. And then you could also have embeddings. You could learn word embeddings through autoencoders. So just by the process of reconstructing the inputs, you could learn word embeddings, which are very useful on downstream tasks. You could analyze sentiments. You could do something called world models, which is a very new research in reinforcement learning. What it does is it trains an autoencoder to essentially dream of, let's say, a game. So let's say you want to train an agent to play a game. And what you do is you have an autoencoder in that agent which is trained to reconstruct the states of the game which it sees and the future states. So it sort of dreams up these imaginary scenarios that could play out in the game, and then it trains from those scenarios. So instead of real time playing, it plays in its head, which is a lot faster. So it's along the general theme of model based reinforcement learning. And also you could have something called one class classification, which we already talked about. And what it essentially does is, suppose you have a disproportionate amount of one class out of two. So let's say you have fraudulent credit card transactions. So out of a million transactions, maybe a few hundred are fraudulent. So very, very few number of classes of one category as opposed to the other. If you train a regular classifier on this, the classifier would almost always predict the benign class because it's been exposed to too many examples of this positive or benign class as opposed to the fraudulent cases. So it learns to ignore those fraudulent cases and always map the input to the output, the positive output. So there's a disproportionate amount of data. What you could do is you could train an autoencoder on this, and that could learn a latent representation, which makes it easier to classify those fraudulent cases. And now this is the latest application of the autoencoder. It's called DeepFakes, and chances are you've heard of it. Let's talk about it. I won't go into the gory details of deepfakes or what it can do or what has been done and how it got popular. Let's say it's not beautiful by any means, but let's talk about the algorithm behind deepfakes, and I'll probably do an episode devoted to deepfakes in its entirety. But here's the overview. It's a regular autoencoder. Suppose you have two faces, A and B, and you want to swap them. So what you do is you gather two different data sets, one of phase A and the other of phase B, and you train autoencoders on both of these, just like we did for the MNIST data sets. But you do two different autoencoders with a similar encoder, with the same encoder. So two different decoders, but the same shared encoder. So you train it, and the encoder decoder pair of phase A learns to reconstruct the phase A. Similarly for phase B. And after you've trained it, here's the genius. Let's say you wanted to swap phase A for B. What you do is you send in phase A through the encoder, and the encoder has learned how to represent phase A's features as a latent vector. So here's the latent representation. But now, instead of passing it through the decoder A and getting the phase back, you pass it through the decoder B. And the decoder B takes the essential features, the sort of pose of the image, the general features of the image, the shape of the image, the angle the eyes are looking at, etc. All the features which are general to both the faces, it takes those features, and the only thing that the decoder B knows is to take those features and construct the face B. So what happens is this phase is somehow morphed onto the other face, face B. So all the essential features are retained, but the face looks like face B. And this is the genius of deep fakes. Uh, and the details of how it's used, like I said, are not beautiful or elegant by any means, but people have found other uses to this deepfakes algorithm, and one such use is something very interesting that I found. It's by a guy. I'm not sure what his name is. I think his name is Chintan Trivedi. What he's done is he's done the same thing to FIFA's graphics. So if you look here on the left, you see the regular FIFA 18 graphics, and you see Cristiano Ronaldo's face here. And on the right side, you see something which is morphed by a deepfakes algorithm. And what he does is he takes these sort of images, these sort of in-game faces, as one set of faces, and on the other hand, the real faces of Cristiano Ronaldo, that is the other face. So what the deepfakes algorithm learns to do is it learns to map these in-game faces to the real faces. So on the right, you see a slightly more realistic version of Ronaldo. This is absolutely brilliant, and this is the guy responsible for it, Chintan Trivedi. So do look him up. So that's about it. But before letting you off, on this note of reconstruction, let me do something very interesting. Let's fiddle around with this latent space and see what happens. Because what we've done so far is something very boring. wanted to reconstruct an input, and in the process of reconstruction, we have certain latent vectors. So, in the spirit of deepfakes, what we'll do is we'll play around with these latent vectors and see what happens when we pass the modified latent codes to the decoder. Let's see what images they come up with. So, what I've done here is I've sent the decoder a set of linear points in the latent space. So it's a linear interpolation. So we draw a line in the latent space, and on regularly spaced intervals, we sample some points along that line, and we sent it to the decoder. Let me stress that this is not some line. We choose a random direction along the latent space, but what we want is we want this line to pass through a data point on the validation set. So what you'll see is right in the middle of these points, you'll see an actual realistic image which is sampled from the validation data. So let's see what happens. And here it is. On the middle, you can see a realistic validation data image, which is a 6. And when you go to the left or the right, it changes. We slightly shuffle or change the latent code along some random direction. And let's see what happens when we go down. As we go down, the curl of this 6 slightly disappears, or rather the top portion of the 6, the top stroke of the 6 evaporates into thin air, which is very interesting. And on the top, the curl of this 6 vanishes slightly. And I suspect if you go further, it morphs into 1. So this is what happens. And you'll notice something very interesting. If I do this for some set of data points in parallel, and I create an animation out of it, you can see all of it in parallel. So this is what I've done. And you see all of these images are interpolated along the same direction. But in the middle, you sort of recover actual realistic images. And as you get to the extremes, the images are distorted. So what you observe is that this latent space is not dense, in the sense that most points you sample along the latent space do not give you realistic images. And that's worrying, because if we were to, let's say, pass in some random latent code to the decoder, we should not expect realistic images as the output. But let's see what happens. Let's try to generate images by doing exactly this, by sending some random vector as the latent code. So here's a random vector, and we send it to the decoder. Let's see what happens. We get utter rubbish, which is exactly what we should expect, because the autoencoder is not trained to generate images. The decoder should be used as a decoder, not as a generator. Or is it? This idea is what gives rise to what we call variational autoencoders, and we'll see that in the next episode of Notes. So, till then, I'll see you later. Goodbye and good night.